All right, today we're tackling a big one, a real cornerstone of modern networking, OSPF. We're going to break down just how it works, why it's so incredibly smart, and how it really does act like a super intelligent GPS for all your network's data. So let's dive in and see how this thing builds its own map, one connection at a time.
I mean, seriously, just picture that for a second. You'd never get anywhere, right? Well, that's kind of how simpler routing protocols work. They only know about their immediate neighbors. OSPF, though, it's on a whole other level. It doesn't ask for directions. It builds a complete, detailed map of the entire road system before you even think about starting your trip.
And you know, having that complete map is absolutely crucial. Because modern networks, they face this one massive, overwhelming challenge, the problem of scale.
Look, when you've just got a handful of routers, simple protocols are fine, no big deal. But when that network starts to balloon to hundreds or even thousands of routers, those simple ask your neighbor methods just completely fall apart. You end up with traffic jams, constant instability, just a whole lot of chaos. And that's the exact problem OSPF was born to solve.
So here it is, our solution, OSPF, which stands for Open Shortest Path First. Now, the magic words here are link state. See, unlike other protocols that basically just rely on gossip from their neighbors, a link state protocol makes sure every single router has an identical, super comprehensive map, what we call a topology, of the entire network. No guesswork.
So how does a router keep all this map data straight? Well, it uses these three very distinct tables. First, it builds a neighbor table, which is basically its list of immediate friends. Then, using info from those friends, it puts together the topology table. That's the big one, the full map of every possible path in the network. And finally, from that giant map, it does the math and creates the routing table, which contains only the absolute best, most efficient routes to get anywhere.
You know, everything in OSPF has to start somewhere. And it all begins with building that very first table, the neighbor table. Before any maps can be shared, routers have to, well, get to know each other first.
And yeah, it literally starts with a hello. Routers that are running OSPF are constantly broadcasting these hello packets. It's kind of like them shouting, hey, are there any other OSPF routers in the room, into the void? And when another router hears that hello and shouts one back, that's where the relationship begins. But you know, it's not quite that simple. They don't just become friends automatically. They have to pass this really strict compatibility test, almost like a checklist for getting along. If any single one of these things, like their area ID, their timers, or their subnet mask, doesn't match up perfectly in those hello packets, they will flat out refuse to become neighbors. No exceptions.
Okay, so once they agree on all the terms, their relationship grows through these very specific stages. It starts at down, which means no contact at all. Then it moves to init once a router hears another's hello. The really big milestone, though, is two-way. That's where they both confirm, yep, I can hear you and you can hear me. After that, they start swapping their map data until finally they reach full adjacency. That means their maps are perfectly in sync.
So, now our routers are making friends. But just imagine this happening across a massive global network. If every single router had to know every single detail about every other router, well, their processors would just melt. To stop that from happening, OSPF uses this brilliant divide and conquer strategy called areas.
The whole idea here is actually pretty simple. OSPF chops up a huge network into smaller, more manageable zones or areas. Think of it like states in a country. If you live in New York, you need a detailed map of New York, but you don't need to know every single side street in California. To get between states, you just need to know how to get to the main highway system. In OSPF, that central highway system is a very special hub called the backbone, or Area 0.
This whole structure creates these specialized jobs for routers. Most of them are just internal routers, living their happy lives inside one area. The really important ones are the area border routers, or ABRs. They're like the border patrol, sitting on the edge of an area, connecting it to that main backbone. And then you have ASBRs, which are basically the ambassadors that connect your entire OSPF world to other networks, like the big wide internet.
I just have to say this again because it is the golden rule of OSPF design. Area 0 is not optional. It is the transit area that stitches the entire network together. If you don't have a backbone area, the whole system just falls apart, period.
So we have neighbors, and we have our areas, but how do routers actually share map updates inside those areas efficiently? Without just creating a flood of constant chatter? Well, OSPF has a really clever system for that too. Okay, this slide shows a super common situation. Think of an office Ethernet network
where a bunch of routers are all plugged into the same switch. Now here's the problem. If every single one of those routers tried to become full-on neighbors with every other router, it would just be a chaotic, noisy mess of updates. And the math on this gets ugly fast. The number of connections you need just explodes exponentially. With just 5 routers in that office, you'd need 10 separate neighbor relationships. 10 routers? That jumps to 45. It's not going to work.
The solution is so elegant. They hold an election. On these kinds of networks, the OSPF routers elect one designated router, or DR, to be the official spokesperson. So instead of everyone yelling at everyone else, all the routers just report their updates to the DR. Then, the DR efficiently sends out a single update to everybody else. It massively cuts down on all that useless chatter. So these updates, they're called link state advertisements, or LSAs. You can think of them as different types of news bulletins. A Type 1 LSA is just a router saying, hey, here are my direct connections. A Type 2 LSA is that designated router announcing, okay, everyone, here's the list of who is on our shared network. And then you've got Type 3 and 5 LSAs, which are sent by those special ABR and ASBR routers to share summarized info about other areas or the world outside.
Okay, so the routers have made friends, they've organized themselves into areas, and they're sharing news efficiently. Now for the grand finale, using all of that amazing information to actually pick the best path. And this is where OSPF's intelligence really shines. It doesn't just count the number of routers or hops to get somewhere. No, it uses a metric called cost. A path's total cost is just the sum of the costs of all the links along the way, and the path with the lowest cost always wins.
So what's this cost thing based on? Bandwidth? It's all about speed. As you can see in this table, a really fast, high-bandwidth link like Fast Ethernet has a super low cost of 1. But a slow, old-school 56K serial link, it has a massive cost of over 1,700. This is what makes sure OSPF will always choose the fast, direct highway over a slow, winding country road, even if that country road has fewer turns. And the engine, the brain that does all of these incredible calculations, is a famous process from computer science called the Dijkstra shortest path first algorithm. Every router runs this algorithm on its topology map to figure out the lowest cost path from itself to every other place it knows about, and that's how it builds its final, perfectly optimized routing table.
So let's just sum it all up. OSPF is amazing because, 1, it's scalable. It uses those areas to keep giant networks from turning into chaos. It's efficient, using designated routers to cut down on noise. It's incredibly intelligent, using cost to find the genuinely fastest path, and because of all that, it converges or adapts to network changes unbelievably fast.
And that kind of leaves us with one last thought. OSPF was this huge leap forward in making networks smarter. As we keep moving into this age of AI and automation, it really makes you wonder, what's the next step? Will protocols like this evolve to not just map the network, but to actually predict traffic and make proactive decisions all on their own? The foundation for it is definitely there.